In the previous modules we derived conservation of mass, conservation of momentum, conservation of energy, and we had just started principle of similarity. What we will do in this module is we will apply the non-dimensionalization to the momentum equation and the energy equation and come up with all the relevant non-dimensional numbers from momentum and energy equation and their physical significance. This is the objective of this module. Just to recap, we had just written the momentum equation and we said that x star equal to x by L, y star equal to y by L, u star equal to u by u infinity, v star equal to v by u infinity, p star equal to p by rho u infinity squared. What is u infinity? It is just nothing but the free stream velocity for a flow over an external body or an average velocity in the pipe. L is the characteristic length of the flat plate or diameter of the pipe, and we are neglecting the body force. Now given that, let's get the derivation back. So this is what we had written in yesterday's module. So let's not, if I just substitute for u, I need to substitute u star into u infinity, and for x, x star into L. So if I do that, I get rho u infinity squared upon L, because you have two u's here. So you get u star u infinity, so that is u star del u star upon del x star. V and u and y, again we are non-dimensionalizing with u infinity and L. So you will end up getting u infinity squared by L only. So you get v star del u star by del y star. And for p, I have to write p star into rho u infinity squared. So I get rho u infinity squared, and for x, I need to write x star into L. So L gets out. So I get minus of del p star by del x star plus mu into what is there for u? U star, that is u infinity upon x squared it is. So x star squared L squared. So you have mu infinity by L squared into del squared u star upon del x star squared plus del squared u star upon del y star squared plus, let me pull out this mu because we have assumed that the viscosity is anyway constant. So mu, you have u infinity u star upon double x is there, so you get L squared. So u infinity upon L squared into del by del x star into mu by 3 del u star upon del x star. So no, this mu I have pulled out, so this will be 1 del u star by del x star plus del v star by del y star. In the next step, what I will do is I will divide this throughout by rho u infinity squared by L. Okay, if I divide that, what will I get? So I get on the left hand side u star del u star by del x star plus v star del u star by del y star, and this is equal to, I am dividing this rho u infinity squared by L only, so I am supposed to get 1, isn't it? So I get minus del p star by del x star plus mu u infinity by L squared into L upon rho u infinity squared into del squared u star upon del x star squared plus del squared u star upon del y star squared. Similarly, plus mu u infinity upon L squared into L upon rho u infinity squared into del by del x star of 1 by 3 of del u star upon del x star plus del v star upon del y star Now let us just take this term alone, that is this term alone. So what is that I am getting? So I get, if I take only that term, I get 1 upon mu upon rho u infinity L, because u infinity get cancelled out, L and L squared, 1 L is gone. So you get mu by rho u infinity L, but this is nothing but 1 by Re. So same thing here for this. So you get 1 by Re. So if I write the equation now, so I get u star del u star upon del x star plus v star del u star upon del y star equal to minus del p star upon del x star plus 1 by Re into del squared u star upon del x star squared plus del squared u star upon del y star squared plus 1 plus 1 by Re del x star into 1 by 3 del u star upon del x star plus del v star upon del y star. So when we non-dimensionalize the momentum equation, we get Re equal to rho u infinity L by mu, which is nothing but inertia force upon viscous force. Okay. Here we have inertia force, pressure force and viscous force, but here this Reynolds number is a balance of inertia force to the viscous force. So much about the momentum equation. Now let us take up principle of similarity for energy equation. So let's take up energy equation. So in the energy equation, what is our energy equation? Let's write that energy equation. So I have rho Cp del T by del T plus U del T by del X plus V del T by del Y is equal to K del squared T by del X squared plus del squared T by del Y squared plus dP by dt plus phi plus volumetric heat generation. So this is my convective term, this is my conduction term, pressure work, viscous dissipation which is done, that is the work done by the viscous forces, and this is the volumetric generation. So what was phi? Phi was equal to 2 mu del u by del x whole squared plus 2 mu del v by del y whole squared minus of 2 by 3 mu del u by del x plus del v by del y whole squared plus mu into del u by del y plus del v by del x whole squared. Now if it is steady flow, for steady flows del T by del T is 0. Del T by del T is 0. So you get rho Cp U del T by del X plus V del T by del Y is equal to K del squared T by del X squared plus del squared T by del Y squared. Now in this dP by dt, if I expand that, dP by dt equal to del P by del T plus U del P by del X plus V del P by del Y. Now for steady flows, this term wouldn't be there. So you get plus U del P by del X plus V del P by del Y plus phi. Let me neglect volumetric heat generation. Okay. So, with this, now again I will do that non-dimensionalization what I did, that is x star equal to x by L, y star equal to y by L, u star equal to u by u infinity, and v star equal to v by u infinity, p star equal to p by rho u infinity squared, and T star equal to T minus Ts upon T infinity minus Ts. So, again u infinity is the free stream velocity, P is the pressure, rho is the density. So, L is the characteristic length, same as what I had told, and Ts is the surface temperature. Okay, surface temperature of the plate or the pipe depending on the flow situation, whether it is internal or external. So, if I do this, first let me do it for phi. Before I do that, let me do this for phi. Phi equal to mu I will pull out. I am focusing on this portion. I am focusing on this portion now. I am non-dimensionalizing that. So, what do I get is mu if I pull out, you see here u become u squared is there. So, you get u infinity squared and x squared is there. So, you will get L square. So, you get 2 del u star upon del x star squared. Similarly, 2 del v star upon del y star squared minus of 2 by 3 del u star upon del x star plus del v star upon del y star squared plus del u star by del y star plus del v star by del x star whole square, whole in the bracket. So, phi I can write it as mu u infinity squared by L squared. This let me call it as phi star. Let me call it as phi star. So, phi star. Okay. Now, let us get back to my original equation, this energy equation, and substitute all of this again into my energy equation. Okay. So, if I do that, so what is that I get on the left hand side? I get rho Cp. For u it becomes u infinity u star. So, you have u infinity, and for t it becomes T infinity minus Ts, okay, T infinity minus Ts upon x star, that is L. See, how did I get? See, if I write T equal to T star into T infinity minus Ts plus Ts, I am considering Ts is constant. So, when you differentiate del T by del x, you get del T star by del x into T infinity minus Ts. If you differentiate Ts with respect to x, it is constant, so it is not going to be there, and then x gets replaced with x star by putting L here. So, you get u star del T star upon del x star plus v star del T star upon del y star, okay, is equal to k into T infinity minus Ts upon L square, because it becomes T star upon x star square. So, you have del square T star upon del x star squared plus del squared T star upon del y star square plus u infinity, P becomes rho u infinity squared by you have rho u infinity squared by x becomes x star into L. So you have u infinity into rho u infinity squared by L into u star del p star by del x star plus v star del p star by del y star. Okay, so we have non-dimensionalized this. Now let us see what will this reduce to and what non-dimensional numbers we will get. So I have to divide throughout by this term now. Okay, if I divide throughout by that term, so I get on the left hand side u star del t star by del x star plus v star del t star by del y star is equal to k into t infinity minus ts upon L squared into L upon rho Cp u infinity into t infinity minus ts into del squared t star upon del x star squared plus del squared t star upon del y star squared plus, now there was one more term which I missed out here. There was one more term which was missed out, that is for phi we had written down, that is mu u infinity squared by L squared into phi star. That should be there here. Sorry about that. Mu u infinity squared upon L squared into phi star. Okay, so you have u infinity into rho u infinity squared upon L into L upon rho Cp u infinity into t infinity minus ts into u star del p star by del x star plus v star del p star by del y star into plus mu u infinity squared by L squared into L upon rho Cp u infinity into t infinity minus ts into phi star. So we are now, let us focus on this term. So what will happen here? T infinity minus ts gets cancelled out. So let me just write down u star del t star by del x star plus v star del t star by del y star equal to k by rho Cp can be written as alpha and L gets cancelled. So in the denominator I have alpha by L, then you have u infinity. Alpha by L u infinity is what you are going to get. So that is del squared t star upon del x star squared plus del squared t star upon del y star squared plus. So what about here? U infinity gets cancelled out, rho gets cancelled out, L get cancelled out. So we end up with u infinity squared divided by Cp into t infinity minus ts into u star del p star by del x star plus v star del p star by del y star plus, now here you have, what is that you are going to get? So you have mu by rho, you can write that as nu, mu by rho as nu, and u infinity squared, one u infinity is there. So you get u infinity, and in the denominator you have L and you have Cp into t infinity minus ts. Is that right? Yes. So now let us take up one by one term. That is, now let me write alpha by L u infinity can be written as nu upon L u infinity into alpha by nu. What did I do? I multiplied and divided by nu. So what is this u infinity L by nu? That is nothing but my Re, 1 by Re, and nu by alpha is Prandtl number. Nu by alpha Re is equal to u infinity L by nu. Prandtl number is nu by alpha, because of which this becomes 1 by Prandtl number. So, this term, whole of this term becomes 1 by Re Prandtl number, right. Now, next term, let us take up next term. This u infinity squared by Cp into T infinity minus Ts is defined as Eckert number. Within few minutes, I am going to tell you what is its physical significance. Ec means Eckert number. Now, let us take up this nu by L, u infinity, Cp into T infinity by Ts. So, let me multiply and divide this by u infinity, nu L u infinity into u infinity square divided by Cp into T infinity minus Ts. Is that right? So, that is equal to u infinity squared by Cp into T infinity by T minus Ts is nothing but my Eckert, and Lu infinity by nu is nothing but my Re. So, whole of this into 5 star was missing, into 5 star. So, whole of this is nothing but my Eckert by Re. So, let me rewrite this equation now. So, what is that I have gotten is u star del T star by del x star plus V star del T star by del Y star equal to 1 by REPR into del squared T star by del X star squared plus del squared T star upon del Y star squared plus Eckert into U star del P star upon del X star plus V star del P star upon del Y star plus Eckert by Re into 5 star. This is the equation we got. Now, let us take up one by one equation and write once again. Re we have done, but still let us do it. Re equal to rho L u infinity by nu, that is inertia force upon viscous force. So, that tells whether we are in laminar flow, turbulent flow. So, this is Re. And what is PR? PR equal to nu by alpha. What is nu? Nu, I would not like to write here kinematic viscosity. I would like to write this as momentum diffusivity. How do I understand that? Is momentum diffusivity. Alpha is K by rho Cp, that is thermal diffusivity. See, what do you mean by momentum diffusivity? See, diffusion. See, now you see the knowledge is getting diffused through this medium of Arpit. That is diffusion. News channels are diffusing news. Now, if you put in chai patti in your cup, the chayness from the chai patti is getting into the water. That is diffusion. So, momentum gets diffused because of the presence of nu. If nu is not there, momentum cannot. That is, one molecule giving momentum to the next molecule is only through this nu. And alpha, thermal diffusivity means temperature is getting diffused. Thermal energy is getting diffused through this alpha. Okay. So, now Eckert number. Eckert number is u infinity squared divided by Cp into T infinity minus Ts, that is kinetic energy by thermal energy. This is very important term. How much of this kinetic energy gets transformed into thermal energy is represented by Eckert number. It is important only in case of supersonic flows, that is Mach number, that is velocity of the fluid divided by velocity of sound in air. So, that is C is 330 meters per second. So, if you were to take, see Kalpana Chawla, the Colombian shuttle disaster, she died because one of the tiles came off from the space shuttle. because the space shuttle will be moving at a Mach number of roughly 40. How did I come up with this? You have 12 kilometers per second as your escape velocity. So 12,000 divided by roughly, if I take 300 as my velocity of the speed of the sound in air, so I get 40. So the Mach numbers are so high. When the Mach numbers are so high, then all of the kinetic energy gets transformed into thermal energy. The tile came off, so the space shuttle caught fire. So for subsonic flows, that is for subsonic flows, for Mach numbers less than 0.3, Eckert number will be very less. Okay, that is, for example, for a velocity of 10 meters per second and Cp is 1005 joule per kg Kelvin, the delta T, that is T infinity minus Ts, would be of the order of 10 Kelvin. So you get Eckert number equal to 10 square divided by 1005 into 10. So you get of the order of 0.01. So for low speed flows, you can neglect Eckert number. That is, the viscous dissipation term and the pressure work term can be neglected for subsonic flows. So for subsonic flows, your energy equation reduces to U star del T star by del X star plus V star del T star by del Y star equal to 1 by REPR into del squared T star upon del X star squared plus del squared T star upon del Y star squared. So much about similarity. So with this, we have completed similarity and identified all the non-dimensional numbers which you get from momentum equation and energy equation. Thank you.